And thanks for everyone's time. I appreciate everyone who can make it. I just kind of reemphasize my introduction here. I'm Tom Wick. SICK is a company that's been involved with automation for probably about 70 years or so. And where we specifically focus is on applications that are usually done in manufacturing, logistics, process, like oil and gas, things like that. And what we focus on is automation equipment. How do we detect things? How do we protect things like in our safety equipment? As well as how do we get some data out of things that we inspect? So I actually handle a division that's within SICK. My focus is primarily, like she said, around measurement, LiDAR, vision, and ID. They include RFID, barcode reading, and things like that. But really what I wanted to hone in on this presentation is one piece of that on the vision side, on where vision is going, and maybe just use this time to talk about innovations that we see in the vision space and how it pertains to manufacturing and other places. And we'll go from there. We'll use questions at the end. So let's take a look at what vision is. And really what vision is providing is it's an inspection tool that's mainly used in manufacturing to provide things like quality control, part defects, and things along that nature. So typically what you would have is a camera. It snaps a picture of a part, let's say, that we're trying to do some inspection on, and it provides a lot of flexibility in areas where it might be cumbersome for just, let's say, a standard sensor to look for. So let's say, for instance, you have a part where in your manufacturing process you can't really localize it too well, and as it walks across this different area as we're trying to do the inspection, with a camera we can actually put a field of view on it and be able to track that. You can also use that to gather some data. Let's say if I had a robot that's picking parts, I can use a camera to be able to localize where the part is and use that as a way to pick out of a certain position that might be randomly placed. I can use it all for measurement, as far as in the example we show, looking for threading, let's say on a bottle or something along these lines. So vision typically falls, I would say, in four buckets, right? We're trying to position something, find where that might be. We might be trying to inspect that part and look for some type of defects within the part itself, trying to measure something, or we're trying to read something. And then when we're reading, we might be looking for a barcode or something along those lines. So basically the vision market's broken, I would say, into two general areas. First area we have is on our 2D vision side, and what we're doing on the 2D is basically what I just highlighted before. You would have a camera, snaps a picture of a part, and what the example that we're showing is trying to match a pattern. So I just wanted to make sure, let's say the SICK logo was printed on this poker chip that we have highlighted up there. And so I'm using the 2D inspection tool, in this case a square, to highlight where those letters are and make sure it was printed properly. What it's using is an intensity scale to find it. So, there's a internal light that's actually on the camera itself. When it actually takes a picture, it flashes the light, and then the lighting is used to be able to discern which features are there or not. So in this case, the SICK lettering is actually written probably in a white lettering, and so we're looking for the intensity difference to be able to see that difference of the lettering across the background that's in black. We're starting to see actually vision move into the 3D side, and what we're seeing on the 3D side is rather than using light intensity that's susceptible to things like how the light is actually coming from the camera or what the color of the target might be, we're using 3D to actually generate a full three-dimensional image out of there. So they call that a point cloud. And to give you an idea of what that point cloud looks like, I'm just going to toggle over here to an actual setup that I have already loaded. This is a point cloud. So what I'm doing actually here is I'm moving this piece around. We're actually looking at a target. I can actually rotate it in 3D space. And what it is it's actually a box of tea bags is what we're looking at. So what we did is we were able to generate what we call this 3D point cloud, and what you're looking at is the top of the bags actually within the box, And those are representing actually pixels that the camera, the three-dimensional camera, has looked for, and then populated into a volume so that we can look for the actual physical bumps. You can actually see the physical bumps that are actually coming out of this as I rotate it. Now, the reason why it doesn't look like a nice pretty box with tags in front of it is because there's some data that's missing, and that's a limitation of some of the 3D technologies that we have, and I'll get into that in a little bit here on the presentation. But, you know, we have actually a laser that scans across the top of this, and that laser can't return into the camera, and so we actually have some blanks there. So what does 3D do for us? What's the advantage for it? A lot of the times with normal vision, when you're looking at a 2D vision camera to actually look for defects and things like that, you're really depending on a lot of the lighting situations. So when you take that picture and you actually take a flash of light on it, it's going to reflect in many different ways depending on what the part geometry looks like, what the color of it is, what the surface finish is, and so on. What 3D does is it provides that point cloud, so you actually see, it adds depth to the image, think of it that way, where with the point cloud now you actually have multiple bumps that are sitting upon each other, and so it makes actually looking for the part, let's say the top part here, quite easy. So when we took the picture, you can see it's a metal piece on top of other metal pieces, and it might be extremely hard to discern these edges when we're taking actually a picture of it in 2 dimensions. When we scan it, we can actually put this bump up with a point cloud and be able to discern that quite easy. That has very big uses in areas like this. Like here we're showing a missing gasket in a small piece, and it makes it very difficult for a 2D camera to see, simply because the gasket color is the same color as the plastic seat that it's sitting in there. But with the point cloud, we can pull that out, and you can actually see the physical bump jumping up there in comparison with the notch that's behind it. Here's some we see more in a consumer goods type of environment, but very similar type use case where you have black candy actually in black molds. Maybe you want to make sure that every candy is there where it's supposed to be. And that can be what we call a content verification application. So, you know, it doesn't have to necessarily be chocolate. It could be parts in a box. It could be components on a board. It can be many things. But again, what it does is it takes the color out of it. And we're looking at point cloud data. Here, actually, we see a 2D camera. Maybe a customer would want to be able to see this letter that's inside of it, but because the light is, since it's sitting actually in a pocket, we can't get the light down in there to reflect back properly. So with the laser scanner can penetrate that much easier and actually see the bump of the A coming out. So 3D provides not only an advantage from a lighting issue, but because of the extra data that's put into the scan, we can use that to be able to help us see things where it's applications of low contrast and things like that. So let's talk about, real quick, just the different type of technology types. There's different ways that we can get that point cloud. And I'll highlight 4 of them here. These are probably the big main ones. One is we have a structured light type system. So what a structured light is doing is it actually has mainly a projector that actually projects a grid onto a part, and then as that grid deforms, there's another camera that's kind of angled away for it, and it's actually looking for the deformation of the grid to be able to tell the height data. So it gets the height data off of that. We have our stereoscopic 2-camera type devices where it's kind of working like human eyes to be able to discern depth and things along that nature. We have our time-of-flight laser array, and what that does is it actually has a number of lasers that are inside of it. It actually sends out a pulse of the light. It actually times when the light leaves the transmitter on the side and is received by the camera in the middle. And then we use that to be able to build a point cloud that can involve larger objects rather than smaller ones. And then we also have our laser triangulation method where we actually have a light that's actually put onto the target. Almost looks like a barcode reader with a line, if you want to call it that. Part comes underneath it, we scan it, and then we build the point cloud. What I'll really focus on with this presentation is around our laser triangulation, simply because that gives the most resolution, and we see that most applied in the consumer electronics industry. So I'll talk a little bit more, highlight into that, and then touch upon the structured light and time of flight array, since that's what we're seeing more in manufacturing in general. So here's how triangulation, laser triangulation works. So typically what you have is you'll have a sensor head like this, some type of body that you actually put a camera into with your laser line, and what it's doing, it's projecting the laser out of it, and then it's triangulating back into the camera. So there's a chip, it's actually a 2D receiver, it's a 2D chip that would actually sit behind it. And what is happening here is as I move the object up and down, it's actually triangulating back, and it's mapping the chip differently depending on what that peak angle of reflection is. So obviously as the object was moving, that angle is getting bigger, the chip keeps track of that, and as it falls away, it starts to get a lot more narrower. So when we start to talk about 3D vision, we're actually putting a whole laser line across the part. What we're representing right here is actually the map out of what the CMOS chip would look like. As we put that through there, we're actually taking a look at the reflected peak coming off the target. It's coming back into the chip, and then we're reading it across the map. So that's how we get our actual height data. And then actually within the head itself, we're using this to build up a profile. So here what we're showing is we have some type of target. We have some laser light source that's actually reflecting off the target. And so as I actually move that part, you get again to see the profile that it's making on the chip. We actually take those profiles together, and then we build our point cloud data. So it's what they would call a stitching of the different profiles there. And typically we time that with an encoder. So let's say if there's a conveyor belt, parts are moving on a conveyor belt or something along those lines, we would actually time when we are taking those different types of profiles, so that way we can take into account any different types of line speeds or things like that. So typically we would see people use an encoder. They'd time it with a photo eye, so you would have like some type of sensor that would detect the target as it comes in, starts to build those profiles up, and then once we discern how much time how many pulses we want, it stops and it builds up the point cloud. So when I showed that image earlier, that's actually how that was done with one of these type of devices. Typically you have a field of view, right? So again, when you have your laser here, you'd have your camera back here, and depending on how the triangulation occurs, you can either have your image too close or too far away, so it has to be in a certain range in order for that laser light to receive back. So this has something to do with some of that lost data that I showed on the point cloud. They call that occlusion. We're getting some occlusion because we're losing the laser line back into the actual camera housing to see it. And so you actually have a field of view requirement. So in this type of device, which is kind of what you would call an all-in-one head, it actually takes the laser, takes the camera, mates them together, and it's very easy to integrate. So you can basically take this type of housing, mount it on something. As long as within your field of view, you don't have to worry about any type of angles in between the laser line or the camera, and it makes it very ease of use. So where we're seeing 3D technology going is really in two areas. One is going into an ease of use standpoint where the applications aren't extremely difficult, and you can take your device and mount it and then do some very simple algorithms to detect the part. And other ones where you can have complete freedom to mount your camera, to mount your laser wherever you might want to have that, but it gives you extreme flexibility in any application that you might be working on. So you can choose your laser light pattern, you can choose what type of lensing you want on the camera, and it allows for very fast speeds and so on. So I'll show the difference there. So this is a good example of the ease of use version, and SICK actually has a few products that have different field of views. But the software that I was showing before is actually a version of this. And I'll just kind of highlight that very quickly. So again, this is kind of our point cloud data. Whoop. This is our point cloud data. So again, you can see as I'm rotating this on and off. And maybe a typical application that we might see for this type of device for 3D is something along the lines of, I'll go back to content verification. How many parts are in the box? So this could be a very difficult application for a 2D camera to do, simply because of the color. So if I have actually white, let's say, tea bags in a white box, sometimes because of the glare, the lighting issues, if I use a standard camera to take a picture, it might miss a count simply because we can't see a nice edge because the colors are so close and you have low contrast. So here you can actually see the bumps. I can actually rotate this like I did before. You can actually see the physical bumps due to the point cloud. But here's how an inspection might work. What I'll do is I actually register this image. I say this is my image that I want to actually do my inspections on. We come up with what we call a tool set. The tool set will now allow us to do some inspections on this point cloud. So I'll do what we call a tool that actually looks for the different types of what we call a blob, which is mainly a collection of pixels. And what we're doing here is you'll see this yellow actual volume here come up. And what we're doing here is I can actually rotate this, but I can actually change my what we call a volume of interest. So if you remember when I showed the 2D camera, you had that little square. Well, now we're actually looking at a volume versus an area. And I can do things like say, well, I don't want to see the bottom. I'm going to bring this guy up, so maybe I'm just really interested in the tops of the bags versus any type of data that might be behind it. And I can use that to really focus and localize in on a particular area. So the advantage that 3D brings to the table is that, let's say if I did have some white targets underneath here or whatnot, camera's going to have a heck of a time trying to discern the difference between the two, simply because it's only taken that snapshot. With the 3D, we have a volume we can work with. So what 3D does is it brings volume to the inspection, or I should say depth to the inspection, which enables us to get a much cleaner read rate. I'll highlight it with this. What we're looking at here is this actually is we're looking at a contact lens case, and in one image, the actual lens cap is tilted. So, this is very, very common application, let's say in the consumer goods industry, where maybe they want to make sure a cap is sitting right, or they want to make sure a part is properly seated, something along those lines. With a 2D camera, and again, what we're looking at here is the top of the contact lens case, and we're looking at maybe, let's say, a 2D view. So a part could be on a track or something like that, and we have a 2D camera that's looking over the top of it. And maybe I want to discern if that cap is sitting properly. For a 2D camera, you might need to look at multiple 2D cameras to look all over this to detect it, but with the 3D, it really brings a lot of ease of use to try to detect that, so you can actually see that lens start to pop up and back. So what could be a very challenging 2D application makes for a very easy 3D. So these are applications that we're seeing more on what we call our configurable cameras. Again, it's a kind of a housing camera where the camera and the light is all on the one, actually in the one housing. And we're using 3D for what we would consider very simple applications. Is the part sitting there or not? Or is it present? Or is it in the right position? Things along those lines. So moving on, this is an example of what we would see as a streaming camera. So this is a lot more complex than what you saw on the other one, meaning that you have full functionality to your application. So with the other type of camera, you had some limitations as far as the field of view. Maybe you also had limitations as far as what the scan rates are and things like that, enabled to control how fast the parts can move underneath it. With our streaming cameras, this actually brings a new level of technology where you can actually choose which lens you want to use. depending on the field of view, so we can see very, very small objects, for instance. You can choose what laser source you want to use. So you might, in this example, they're showing a blue laser where you can get a lot more detail out of your target. And you can actually have full freedom on how you want that geometry to be. And why that's important is because in some applications that you're working on, if you remember on the point cloud that I showed, it was showing some of the gaps in the data, where depending if you change this geometry, sometimes you can minimize those gaps, or perhaps put two of these together to create a longer laser line, or whatever the case might be. So the streaming data camera is actually something that we see used for people who are trying to integrate a much more sophisticated solution, but this really shows the highlight of where the technology is going. And really, it's centered around three different areas. One would be the speed. How fast can we get a point cloud data? How fast can we get that scan? Two might be the resolution. How small of an object that can we see? And the third one being the dynamic range. So, a lot of these parts, let's say they're on here, might be extremely shiny. Some might be very dark. So when I take my scan, for a given intensity level, how do I make sure that I'm getting both the dark objects as well as the light objects in the same scan? And so these cameras are really starting to push the limits of being able to do that. Kind of an idea on some specifications. SICK has been involved in this industry for a long time. This is our older camera here that's probably been around for a decade or so. We just released a new version of this, and everything's just getting faster. So our scan rate is about 10 times faster. How many pixels we have in the chip allows us to see much more smaller detail, and we got more light sensitivity that's providing that greater dynamic range. And here's an example of maybe where we would show that. So this is actually an application this is a real world application. What we have showing here is a camera. So here's the camera I just had on the previous slide. It's actually mounted in this protective piece here. But what we're doing is what the application is, the customer actually wants to detect this bolt. They just want to make sure that that bolt is properly placed. So we're actually taking this scan. There's a number of these cameras actually put in here so we can get this full field of view. But what they're doing is they're detecting here. You can actually see it scanning across. And that's what the image looks like when the train is moving at full speed. So it's moving, I don't know, maybe 60 miles per hour or so, maybe 50 miles per hour, somewhere right around there. And with that, we can get that type of image. Now, you can see the color here. What the color is basically meaning is how far away it is. So it's not true color, obviously. But what you're looking at is the redder it is, the farther away it is, and and the bluer it is, it's closer. So I should say UV-ish, I guess, purplish. But we can see this little bolt here at that speed, and that shows you some of the capabilities where the cameras are starting to move to in this 3D technology piece. Here's where we're also seeing it, especially in semiconductors like solders and things like that. This has been a very challenging application for us for a long time, and simply because, the geometries get very tricky. So where's that laser reflection going is if we put it at a certain area, are we able to get a good reflection coming back? And so with the Ranger 3, which is our new product, it's actually starting to, with the dynamic range, it allows us to take into account maybe some flashes and glare because the geometry just focused a lot of that laser light back into the camera. And what we're able to basically deal with now is very different changes in lighting. So if the laser kind of focuses away, it becomes very dark. If it comes back, it becomes very bright. And so the dynamic range helps us kind of keep into account. And so we're using it a lot more for applications like this. And it's just simply because the technology is moving to a point now where it can be able to handle it. So moving on, let me just show a different type of 3D technology here. I really was banging the drum about the laser triangulation. But we're starting to see 3D being used in other places other than just doing some extremely fine, detection or measurement or things like that. And this would be a good use case for it. So this is the time of flight technology I talked about earlier. And what you have is you have this rectangular device here. There's actually a whole mess of laser diodes in it, but what it does is it uses a time of flight technology. What that time of flight technology basically is it's sending a pulse of light out, it's hitting a target, and then it actually times it or it actually times from when it left to when it gets back in order to know the distance. So we actually have an array of those. It's sending all these points out. You can see it hits the target, and basically we use that to build the point cloud. So we're still working with a point cloud, so to speak, same type of idea there. But where we see this type of technology being used more of is for bigger locations. So if we're trying to, let's say, map out a room or something like that, or if you have a robot that needs to travel around and see things, you know, we see it used in collision avoidance. We see it used in maybe localization. What they're highlighting here is maybe a place where we're looking for a pallet, and again, for a 2D camera, it's extremely hard for them to be able to do this application very well because the colors and the contrast are so very similar from the pallet to the box. So we actually have a camera that's sending an array of light out, it comes back, we get our point cloud, and then we'd be able to put something very similar that I did on the other software where I detected the tea bags in the box. We can use that to be able to detect and say, hey, is there a box there? Is it present? Or maybe what we would have is a box full of parts, and we just want to verify that, hey, is the parts in the box, something like that. So we don't need extreme amount of accuracy, and these guys really typically don't have the extreme amount of accuracy that you would see like in the laser triangulation. But if you're looking for a large area and you're looking at bigger targets, this is something that we're starting to see come about quite a bit. And that's kind of what the point cloud might look like. So, you know, the resolution is, you know, might see details such as the arm of a chair and things along those lines. But, you know, what we might be lacking is the actual detail in the arm. The other thing that we also do in this type of technology is we'll take an actual picture of the target and interlay the intensity value 2D picture on top of the 3D point cloud so you can get a much better representation of what you're seeing and things like that. And that's one of the things that I'll really hit upon with 3D technology is that we're starting to see a lot of the 2D technology migrate into the 3D. So with the intensity data that we can get on the point cloud, we'd be able to do things with a normal camera used to be able to do. You know, so let's say if, for instance, there was some writing on these boxes, and I wanted to make sure that that writing was there or something along those lines. We can do that on one device rather than having one device look for the point cloud and one device look for the 2D data. We can actually do it in one device. So a lot of what we would say the 2D tool sets moving to the 3D.
Time of flight and triangulation techniques, you guys have a metric or rule of thumb in terms of how much do you divide your field of view into, you know, what grid? If I want to measure something at a certain distance, what resolution can you resolve? Your point cloud resolution.
Yeah, so you want to know at what distance what resolution can we get at what distance?
Correct.
Yeah, so we would actually have tables on that. So for instance, if we look at the laser triangulation method, we would actually give you a specification of resolution depending on where in the field of view you are. So in cases of like the ease of use device that I showed, there's an actual spec in the field of view that tells you what that resolution would be.
So what are those rough numbers like in the market today?
So if you're looking, let's say, on a triangulation type sensor, typically that would be, if you're using a really extreme tight field of view on that streaming camera, we can do submicron. If we're looking at that other one, the ease of use, it's typically on the scale of about 10 to 20 microns, depending on the field of view. So if you remember, there was 3 images up there with different field of views. Resolution suffers the bigger you get.
So the optics will determine that. You mean?
Yes, correct. It's the optics in the CMOS chip. So if you remember, what you have is you have a laser line that's draped across your target. There's a CMOS chip with a certain amount of pixels across it, for instance. you have to divide that from the amount your laser line is, and that determines your resolution, let's say, in the what we would call the X, along the laser line. Our best resolution is actually going to be in the Z. So what that height data is, that's where your best is, because just the way that the resolution scans across it, that's the tightest. But
what is the 2D resolution of this this snapshot? Okay. What's the 2D resolution of this? How many points does
I
it
don't
set
know
up?
the answer to that specifically. My gut feel is on the device is it's probably about a VGA image, 640 by 480 roughly.
Okay.
The pixels, the actual point cloud itself is much less. It's probably about 320 pixels by 320 is what you're looking at. So you're not getting extreme high resolution with these, and so that's kind of why. And the reason for that is because if I go back to this, what we have to do in order to get that resolution is we have to put all these laser diodes actually into the device, and that generates a lot of heat. So you're right now as it stands, that's kind of why you see these big fins on it, see all these fins that are on the top. That's being used to dissipate the heat off the device. And so if we put a lot more in there, we can get a lot more resolution, but it'd be really big and large. So that's kind of where this technology stands at. But what's nice about this technology is a snapshot. So you don't have to have moving parts. Whereas the laser triangulation technology, it's actually a moving part that's coming across. Does that answer your question?
Yeah.
Okay. So let me just talk a little bit about robots, where robots are becoming a big thing here, and we're starting to see it used quite a bit in manufacturing. And 3D is becoming a big player in that. So I'll talk here about part localization in bins. That's probably another big area where we're seeing it. So what we basically have here is we have actually a robot. We actually have a bin with parts that sits below it. There's some type of gripper that sits on here. And we have some type of device that's actually looking inside the bin to determine the parts out. And really what's becoming a big player in this, in manufacturing and even logistics, is having a robot go in and take a collection of parts and organize it. So you'd have like disorganization of parts, maybe they were machined or maybe they were die casted or something like that, and then they need to be machined. So you need to take them out. Typically in the past you see an operator who's pulling it out and doing these type of things. So robots are becoming a big part there. And the challenge with this is, as we automate this process, is what we want to do is be able with the point cloud to look for these parts that are there and then know their orientation, know where they're placed, so that the robot knows how to go in and make what is called a pick solution. So where does it grab that part? It has to actually orientate the gripper a certain way. So how is it going to orientate that gripper? And so we see 3D being used quite a bit in this case. And what we're showing here actually is actually a 3D scanner, and there's two different types of scanners here that you can choose from. One is the laser triangulation, the other one is the structured light. And then that's being fed back to some software that's actually taking the point cloud data and matching it with some CAD drawings that might have been downloaded into the device. And then it does a comparison. When it does the comparison, then it knows how it's orientated, and from there you can basically tell the robot how to pick it. So in this situation, we have two different types of devices that typically do that. Here's the laser triangulation method that I spoke of before. So what we actually have is it's a bigger device. It's kind of like that ease of use where the camera and the laser pointer are actually in the same housing. And what it's doing here is there's an actual moving mirror that will come across and sweep. So it provides a sweeping laser. Nice thing about this, you don't have to have moving parts. Right? The bin can stay stationary, and then this actual laser would scan across it and then be able to sweep all the parts in there. So it's still building the point cloud the same way that I showed on the previous slides as far as building up profiles, stitching them together to get a point cloud. But what's nice about this is it provides a huge field of view. So if you have some large parts that are sitting in there, and we see this quite a bit in automotive, for instance, it provides a big sweep where we can see these big parts. This one up here is actually the structured light. So again, and to kind of recap what I said earlier, what you have as structured light is you got 3 different cameras here. One is actually projecting a grid pattern that's onto a part. The other cameras are actually looking for the deformations for that grid pattern. What you tend to, actually in this situation, what you typically have is some limitations on field of view. You actually have to be quite tighter to the area. But what you lose in field of view, you actually can pick up in resolution. So we can actually see smaller parts with this structured light system as opposed to this laser triangulation system. So again, the type of technology used to get the point cloud, to do the analysis and that sort of thing, is all dependent on what kind of application you have, and that will tell us what kind of device to use in this. So again, we have to know things of how small the parts, for instance, how close are they packed together, you know, even what the part finish would look like, things like that. So, and then typically, point cloud would look something like this. So what we're showing a bin of parts. Here's the point cloud again. We've generated that from, I'm not quite sure which device this is. I'm pretty sure it's probably a laser triangulation method. But we swept it. We're able to see where this is. So what the software would do now is actually compare the point cloud to the CAD drawings, and then it will actually be able to, it will build these bounding boxes around it to know exactly the location of where these parts are, and then it tells the robot how to pick it. So where are we seeing 3D? We're seeing it pretty much across many different industries. You know, this is an example of maybe some solder, actually some solder scans that we've done with our Rangers, some of the streaming type cameras, and you can see how maybe we're just trying to get a count here. We're actually trying to discern if it's present or if they're broken, something along those lines. We actually have a picture here of one that we did where this is on a ball grid array, and again, we're using this. You can actually see some of the high resolution that we're getting out of this device, and some of the measurements that we're actually getting. So we can get pretty tight and really focused in on specific areas. And again, since we're using this is a 3D point cloud, we're actually using the point cloud data to do the measurement, which would be extremely, extremely hard to do with a 2D camera. Here's some defects. You know, maybe we're just looking for a good versus a bad part that's been put on a board. Maybe we're looking for some broken components, and you can see the good versus bad. So we might just be looking for defective things, not just trying to measure it, but actually looking for some quality control type applications to this. And we're seeing this across all different industries, you know, so bottle count. Maybe we want to just make sure that the correct bottles are in a package, kind of like what I did with the tea bags. You know, we've had applications where they're using 3D data to be able to see if the seal is good, because there's a certain pattern or shape that it brings to the table, and we can actually see that in 3D. Here's the cap inspection. That's a big one in consumer goods, and one that I kind of highlighted with the contact lens case. Here's more applications, you know, what we've seen, and again, it kind of goes back to the black on black, silver on silver, you know, extremely hard applications, extremely hard products to detect, and with the 3D, it just makes it a lot easier, where you don't actually have to worry about putting multiple 2D cameras around or making sure the lighting is right or anything along those lines. So 3D makes that much easier. And with it, that's it. I thank you for everyone's time. Is there any questions?